Today we want to finish up parameterizing this cycloid. We had broken this problem down into parts. We wanted to first we started by parameterizing a circle, and then noting that we want to move the center up to a y value of 1. That's easy enough to do. But then we had to make the x-coordinate roll along with the circle. So we started with our normal parameterization for a circle, which is x is cosine of t and y is sine of t for t between 0 and 2 pi. This will take a circle around once, but it starts in the wrong place and goes in the wrong direction. So if I have cosine of t and sine of t, radian, parametric. Oh, I turned it off. There we go. Cosine of t and sine t, that starts off over on the right point and then goes counterclockwise. So we don't want it to start off on the right, and we don't want it to go counterclockwise. We want to make it turn the other direction. So here's a few things that we want to note. We decided that we wanted to make this circle start at the bottom. We wanted to change its direction, and we wanted to change its center. The center just has to, we want to take this whole circle and move it up 1 unit. So we want to add 1 to all the y values. So if I go up into my y values and just add 1 to all those, that'll send the circle up 1 unit. That's how we change the center of the circle. Here, the circle is going to be at 0 and 1. But it's still, if you note, started off on that right point and went counterclockwise. So let's take a look at the table that I wrote showing the counterclockwise motion and the clockwise motion. Here is a table with our counterclockwise motion, starting off at 1, 0, then 0, 1, then negative 1, 0, 1, 0, negative 1, and 1, 0. What I want to have happen is I want to start off at the point 0, negative 1. So notice that the x's, the x coordinates of my points go 1, 0, negative 1, 0, 1. And my y coordinates go 0, 1, 0, negative 1, 0. I want to do 2 things. I want to reverse those roles. I want the y to start off at 1 and the x to start off at 0. I want this down here. I want the x's to go 0, 1, 0, 0, negative 1, 0, 1, 0. And I want the y's to have the 3 1s and then the 2 zeros. So we notice that the x's and the y's, the x's that I have do the opposite of the y's, the x's. Sentence is difficult today. Don't know why. The x and y coordinates are doing the opposite of what I want them to do. So one strategy we can employ is to just go switch our cosine and our sine. Based on the observation that the x's are 1, 0, 1, 0, 1, and the y's are 0, 1, 0, 1, 0. I want to switch those around. So let's see what happens if I just switch the sine t and cosine of t. Now it went around the right direction, but it started off at the wrong place. So by switching the sines and cosines, I switched the pattern. This 1, 0 became 0, 1. And then this 0, 1 became, well, it became 1, 0 because we were going the right direction, but we started off in the wrong place. I don't want to start off at the top of the circle. I want to start off at the bottom of the circle. So I want to flip my y values over, but only the y values. I don't care about flipping the x's. So if I go into my y's and I multiply by, I'm going to see what happens if I just multiply by negative 1. Because we know that when we're dealing with a graph, if we multiply all the y's by negative 1, this will produce a reflection across the x-axis. Whoops, that put it all the way down at the bottom, because what happened was I multiplied the 1 by the negative 1 as well. That's not what I want, but so I'll get rid of multiplying everything by negative 1 and just multiply the cosine by negative 1. Oops, now we're going counterclockwise again. Oops. So now I lost my train of thought. What were we trying to do? Oh. So if I just multiply by -1, now we're going the wrong direction. But look where we started. We started in the right spot. We started at the bottom, but we went in the wrong direction. So our x's went from 0, positive, and then negative, then back to 0. That's not what we want to happen. We want the x's to go the other direction. Our y's are doing just fine because we started off at the bottom, but our x's were going in the wrong direction. How can we change the direction on the x's? We could do the same thing. Go into the sign and multiply by -1. Now the x's will go the other direction. Now we start off at the bottom and we go around clockwise. This all goes back to our understanding about how operations affect graphs. When we multiply by -1, we reflect a graph. If we multiply the x's by -1, then we will reflect about the y-axis, because the negative part of the x-axis becomes the positive part of the x-axis, and vice versa. If we multiply the y's by -1, then the positive part of the y-axis, top, becomes the negative part of the y-axis, the bottom. So multiplying by -1 produces a reflection. The advantage that we have here in parametric equations is that we can just flip one or the other, because we're not writing x and y. We're not writing x and y as a relationship with each other, or one as a function of the other. We're doing them individually. So if I wanted to start at the bottom, I needed to have 1 minus cosine t. But if we have positive sine t, then we saw our x's go up, down, and then up again. I don't want that. I want the x's to go down, up, and then down again. So I'll just flip the x's. Any questions? How's everybody okay? Really what parametric equations are, it's just Etch-a-Sketch. We have x on one knob and y on the other knob. I don't bring that up as often anymore because I'm not sure everybody understands what an Etch-a-Sketch is. So Etch-a-Sketch was a toy that came out in the long, long ago. I'm not even sure when it came out. And it's just, you can make drawings and you control 2 knobs. One of them will only move the cursor left and right, and the other knob will only move the thing up and down, and it just makes a line. So if you turn them both, you can just make straight lines up and down. If you turn them both at once, then you can make it go off at angles. And some people, and it all has to be one line. And then if you want to erase, you have to erase the entire thing by just shaking it. And then the Etch-a-Sketch went away. Then the movie Toy Story came out, and I think there's an Etch-a-Sketch character in the Toy Story. And so people knew what an Etch-a-Sketch was again. Toy company said, oh, I bet we could sell some of these. So they sold some again. And now I think they're going away until, I don't know, Toy Story gets rebooted. I don't know if that's going to happen. Maybe Disney will get a hold of it and do a live action Toy Story, which will be animated, just like Lion King. Lion King was not like a live action Lion King. It was still animated. They didn't have lions as actors. So anyway, what are we talking about? Oh, yes. So now I've got the circle doing what I want it to do. It starts off at the bottom and it is going counterclockwise. The last thing that we have to do is make our X, the center, move along. Now, if I just insert a constant, I'm going to change my, I'm going to subtract. If I just insert a constant, that's just going to move the whole circle, but I want the circle to move. I want this thing to roll. So what I want to have happen is I want the X coordinate of the center to start off at 0 and end up at 2 pi. Because that's the circle rolling. I want to move the center of the circle the same value as the t. So instead of using a constant for the center of the X coordinate of the center of the circle, I'm just going to use t. And that's going to start the center at 0. And then as t goes up to 2 pi, that will end the center at 2 pi. And so that's what we wanted to have happen. So here's our parameterization for our cycloid on a unit circle. Now, this is not the only way we could have parameterized this circle. There are other things that we can do. The reason that it worked out this way is because I set up the t from 0 to 2 pi. So one of the good parts of parametric equations is that we have a lot of ability to adjust how things show up. We're assigning some kind of direction or orientation to our curves. They have a starting point, a ending point, and a direction in between those things. We have a lot of freedom about how we assign those values. So for example, if I didn't want to go all the way out to 2 pi, I wanted to just go to pi, I can just try changing. See, if this changes things, I'm only getting half of my cycloid. But what if I make the sines and cosines go through twice as fast? Now the periods of sines and cosines, now the period of sine and cosine will go through around, will be pi instead of 2 pi, because I want the t's to go twice as fast. I have adjusted my inputs to be 2t. So instead of my number line being 0, 1, 2, 3, 4, my number line in the same space is 0, 2, 4, 6, 8. Let's see what happens. It's like it like curved at the end. So we didn't get the right thing. This is because the center is not moving like we want it to move. Because the other thing that we didn't adjust was where the center of the circle is. So in the beginning, the center of the circle is t, but it's not moving all the way out to pi. What if I do the same thing to this t? Now I get the cycloid that we want. Because when we plug in t equals 0, we were starting at the right spot, 0, 0. But for those small values of t, we weren't subtracting the right amount. We had some small value of t, and when we subtracted sine of 2t, we were subtracting more than the t that we had. So that's why I went backwards a little bit. So now I've got everything moving at the right speed. Any questions? Now, let's see. Oh, no, I wouldn't be able to parameterize with different parameters. So if I go down to this green one, I can't remember what the next thing I wanted to do was. So let's see, let me put these in again. So notice, you can't really see it. I was worried that this wouldn't be able to see. Notice that the first half is showing up green and the second half is showing up as red. So that's because I'm only plotting values of t between 0 and 2 pi, or sorry, 0 and pi. If I go back up to 2 pi, notice that I get one cycle of the cycloid in the green, but also there's a little bit more red going on over here. So if I window, and let's just scoot this over 6 units. So there's the 2 cycles of the cycloid in red, and then 1 cycle of the cycloid in green, because the red cycloid is going twice as fast. So we have a lot of control over how we parameterize curves because we can make adjustments to the parameters. So here I'm going from -2 pi to 2 pi. That's giving me 2 cycles of the green cycloid and 4 cycles of the red cycloid. Any questions? Let's turn this one off. Go back to, that's fine. We just have the green one. Let's suppose that we wanted the cycloid underneath. I didn't want the cycloid to be above. I wanted a cycloid because we wanted to put beads on it, and we want the beads to roll down at the same speed to the bottom, or in the same amount of time to the bottom. So if I want to flip things over vertically, that means I want to change the sign of my y values. So I'll just take the 1 minus cosine t and multiply by -1. And then we'll get that bottom part. If I want the bottom part to be a little bit lower, I want to put some space in between, I can just subtract 1 from it. That'll drop it down 1 unit. So now it won't go through the origin, it'll just move down 1 unit. If I want these to be a little bit off center, I can add something to the x and shift this over a couple of units. Because that's what addition does to a graph. If you add to the x's, it's going to shift it left and right. If you add to the y's, it's going to shift it up and down. Any questions? How's everybody okay? What's that? I'm not sure I get your question. Oh, right now my parameter is from -2 pi to 2 pi. If I go from 0, then I'm just going to get that first one, that first cycle of the cycloid. Any questions? Let's turn this one off. Oops. So let's invert things. Let's switch the x's and the y's and see what happens. So now, if we switch the x's and y's, that's going to flip things over the line xy. This is how, if you recall, this is how we make an inverse. To find the inverse of a function, I know that this isn't an invertible function per se, but when we make an inverse, we flip a graph over the line x equals y. X equals y is the line where nothing changes. The x's become y's, the y's become x's, dogs and cats living together, mass hysteria. If I throw in the line y equals x, oh, we're in parametric mode. And I still want to throw in the line y equals x. But y equals x is a function, so I can just make x the parameter, and I can make y the parameter. So now x and y are going to have the same value. So there's my line y equals x. And then the green cycloid and the red cycloid are just flipped over the line where nothing changes. So there's our inverse. And going back to making a reflection over a line where nothing changes. When we're making an inverse, that is switching the x's and y's, nothing happens at any point where x and y are the same, because switching those doesn't change anything. If x is 2 and y is 2 and we switch them around, doesn't look any different. This is the same thing what happens when we multiply by -1. There are lines where multiplying by -1 doesn't do anything. If we multiply the y's by -1, any place where y is equal to 0, nothing changes. Because when y is 0, we multiply by -1, nothing happens. Flipping about the y-axis, making a reflection about the y-axis is multiplying the x's by -1. On the y-axis, x is equal to 0. So when we multiply those values by -1, nothing happens. Any questions? Is everybody okay? The other interesting thing about parametric equations, notice that when I wanted to shift things left and right and up and down, I just had to add or subtract in the direction that I want. If I put +2, everything's going to be 2 larger, 2 to the right or 2 up. When we have a function, when we're in function mode, if I want to shift up and down, since that's after the squaring, that's after we get our shape, if I put +1 afterwards, then the graph goes up 1. But if I put +2 before, just easier to type the whole thing. Oops. If I put +2 before the squaring, this is going to shift the graph not to the right, which is the positive direction. It goes left. Because what we're doing is we're taking the x-axis, and the 0 point where the vertex is supposed to be is not at when x equals 0. I got to make 0 squared. That happens at -2. That's why the whole graph shifts left 2 units. But for parametric equations, here it is, turn this one off. When we added 2 and subtracted 1, adding 2 to the x's moved to the right 2, because we're not doing before the function and after the function. Yeah, if I had x +2 squared, that move. If we add 2 to the x's, that will move everything to the right. So if I have, let's see. So we're only getting this side, 1/2 of the parabola. So let's go from negative 2 pi. Why still round? Oh, it's also a little bit angular. Oops. All right, 1/100th is kind of struggling for the calculator. So now here, I'm just looking at x coordinates and y coordinates. I'm not applying a function to the x coordinates and a function to the y coordinates. So if I go to my x coordinate and just put a +2, I forgot to change the window, so it's going to be slow again. Oh. It went to the right 2 units. That +2 represented right 2 units. Because I was just doing the t and then adding 2 to it, just move things back and forth. I'm just saying, here's the x coordinate, add 2 to the x coordinate, that's going to move things to the right. But if we add 2 in a function, we add 2 and then square, that's going to make it look like the graph, that's going to make the graph shift to the left. Any questions? Is everybody okay? I'm going to change this before I ask too much of my calculator. There we go. Not bad for 90s technology. Good job, TI-84. How's everybody okay? This probably brought a lot of stuff up about how graphs work. It's important to recognize that this is one of the differences in parametric equations. The x's and y's are being described separately. So if I multiply the x's by 2, Notice that by multiplying the x's by 2 and putting the t plus 2 in parentheses, I actually have 2 times t plus 4. That's going to widen things out. Multiplying the x's by 2 has widened things out because I've taken my x-axis. I've taken my x-axis and made it a 2x axis. Any questions? Is everybody okay? I think a lot of times we stop a little bit early as far as analyzing graphs. Mode. Go back to function for a second. So if we imagine the graph sine x, and let's actually look at more cycles. Let's go from 0 and multiply this by 5. Let's look at 5 cycles. That's going to be too many cycles. It's fine. It's fine. It's fine. If I change my inputs, we know that that will change. If I change the inputs to say 0.5x, we know that this is going to stretch out. I'm going through the cycles half as fast. My x's are showing up half as fast. When the normal x-axis is at 20, my half x-axis is only at 10. That's why it's taken, I only got 2.5 cycles here. And if I multiply by 2, my x's are showing up in the sign twice as fast. So I'm multiplying the numbers by 2, then applying the sign. And so that's why I'm getting this horizontal compression. So usually we stop there. We just use multiplication and addition. Addition shifts, multiplication stretches. But there's other things that we could do. Let's take the x-axis and replace it with the x-squared axis and see what happens to the graph of sine. It gets a little weird. So what's happening? What's happening is that we're getting compression because the x's are coming, but not even compression, because the x's aren't showing up twice as fast, where everything just like our axis is coming in at squared. So this is really weird. Let's raise this to the 1/2 power. So now, yeah, 1/2 was very excessive. Now, instead of the x-axis, I'm looking at a square root of x-axis. So pi doesn't show up until pi squared. And for the real weird stuff, flip the x-axis on its, flip the x-axis over. Oh, I can't even do it, can it? This is what we wanted. Oh, we want even more. It's too many, so we can't even see it. Let's zoom in some more. Let's make the window from, let's cut this by, let's zoom in a little bit. So it starts to look a little bit chaotic and we have a very low res picture of what's going on. But what we've done is we've taken the x-axis and replaced it with the 1/x axis. So the reason that I'm getting all this compression is that I have to draw this sine. And as sine heads off to infinity, we just get this infinite number of oscillations. But what we've done by replacing the x-axis with the 1/x axis is moved infinity to 0. So I've got to cram an infinite number of oscillations of sine before I get to 0. And so that's why it gets really jammed up in there. And the calculator is unable to just print like all, but this should just look like a solid block the closer we get to 0. I wonder how bad we can make this. What we're trying to do is draw an infinite number of oscillations before we get to 0, because that's where we're going to find infinity. As x approaches 0, 1 over x is approaching infinity. So at a certain point, we're just going to see a solid block because we have an infinite number of oscillations getting close to 0. Now, if we zoom out, let's take 0 out of it. I've asked a lot of you calculators, so I'm going to give you a break. If we start later on, the oscillations are very calm now. Because now that I moved infinity down to 0, I've got to cram all those oscillations in there. I've only really got to get one more oscillation off at infinity, because that's where 0 is now. And it's going to take us a while to get there. Any questions? Really weird stuff with graphs of input and outputs. We tend to stop with multiplication, operations of multiplication and addition, mostly because it's nice and straightforward. Addition just shifts things, keeps the same shape, moves things left and right, up and down. That works for when we have functions. That works for parametric equations. Parametric equations, it comes out true. +2 moves to the right or up. When we're dealing with a function, there's a relationship between x and y. If x squared is going to be our shape, +2 before the square moves to the left, +2 after the square moves up and down. We also have multiplication. Multiplication stretches or squishes, but there's a lot of things that we can do, and we just need to upgrade our thinking about graphs. Any questions? How's everything okay? Calculator is tired because I've asked it to do a lot. It's like, oh, dude, I just had to draw an infinite number of oscillations as I was getting close to 0. And then you had me do it twice because you had positive and negative values, because it was doing the same thing on both sides, right? It was giving an infinite number of oscillations on one side and an infinite number of oscillations on the other side. Texas Instruments calculator, not very sophisticated. It's like, oh, that's 2 infinite. That's 2 times infinity, which is still infinity. And the calculator's like, oh, dude, I'm just plotting points. Why don't you get all the way off my back about this infinity business? I'm just plotting points. Thank you, calculator. You know what? I'm going to erase, oops. I'm going to erase this weirdo function and put you back on decimal mode. And we'll talk about why the colors of your functions are not in order later. Any questions? How's everybody? Everybody looks a bit stunned. It's because we've had an infinite number of oscillations. Graphing is really cool. If you're wondering why in trigonometry we didn't talk about all this cool graphing stuff, is that it's too much. It's just too much. Next semester, y'all going to be in Calc 2. I don't know if you're all planning on passing the class. Y'all are going to be in Calc 2, and we're going to be doing some integration, and I'm going to be like, oh, partial fraction decomposition. It's like, oh, I'm going to look this up in my calculus book. It's an algebra topic, but it's not an algebra topic that you want to give to an algebra class. You know what I mean? It's like, no, this is not algebra that's good for an algebra class. It's very advanced. Yeah. It's not even that advanced algebra. It's just mechanically advanced algebra. It's not like modern algebra. This is the thing that's going to happen. Some of you are going to become math majors. I know you're all going to become math majors. Like, oh yeah, that sounds awesome. How do you make money as a math major, Michael? You have to advance to the point where you don't care about money. Then you can truly invest in being a math major. Unless you're an applied math major, in which case you want the most difficult undergraduate degree that there is, then off you go. You can work as an actuary, they'll make a lot of money, but you will be working for an insurance company, so there goes your soul. I don't know. But when you become a math major, you're like, oh, what classes do I have to take as a math major? And in America, we came up with fancy names for it and stuff. Oh, I'm going to take number theory. Ooh, number theory. What's number theory? And you start doing number theory, and you're like, oh, hang on, is this just arithmetic? And the professor will be like, oh, yeah. Now join us in groups, rings, and fields. Ah, groups, rings, and fields. And you pick up a book, and what does it say on the cover? Algebra. And like, oh, MF, didn't I take algebra? And it's like, oh, not this algebra. You've got to do algebra again, because it's just algebra again. And he's like, oh, well, at least after this, I'm going to go to real analysis. And then in real analysis, we're going to be like, oh, limits. You're like, oh, didn't I just do this? Is this just calculus? I'm like, oh, no, this is fancy calculus, because we call it analysis. Obviously, it's something else. At least topology has a new name, and it's legitimately weird. Any questions? Or you could just continue and be an engineer and make stuff that's actually useful. No, I have nothing against engineering. I just knew engineering wasn't for me. This is what happens when you're good at math class. I actually wasn't even particularly good at science in high school. I was just good at the math. I was good at math. I got like 5 A's in my geometry class. The A that I got, and then like the 4 people sitting around me. So I got lots of A's. Actually, one of them wasn't even sitting next to me. He was across the room. I was sitting in a geometry test once. The teacher was sleeping up at the front of the class. He always sat down with his arms folded and just talked to us the whole fucking time. I'm like, oh, are you going to write anything on the board? He's like, oh, no, that would require effort. You have to get up and like write stuff. So we're like taking a test. And I'm sitting there taking a test, and all of a sudden this wadded up piece of paper comes and lands on my desk. I'm like, oh, the hell is this? I look over, some dude sitting 4 rows over, because I sat in the back, and it was like clear 4 rows. So you didn't have to go over anybody. And he's like, oh, pointing at it. I'm like, oh, what the heck? I unwrap it. He's like, oh, what is the answer to question 4? Yeah. I'm like, oh, that is a bold move. And then I looked up, he's like, oh, dude's asleep. So I wrote it down and I threw it back. I'm like, oh, why don't I just walk over there and tell you what to write? I don't think he'll wake up. We're good. So anyway, got multiple A's. But this is what happened in the 80s when you were good at math. They're like, oh, you should be an engineer. And being a teenager, they're like, oh, okay, what do engineers do? They make a lot of money after they graduate college. I'm like, oh, okay, I like money. Money's good. I don't have any right now. I would like some of that. Sounds good. I'll do it. And then like 2 years into an engineering degree, I'm like, oh, what is it that engineers do? And like none of my fellow students could tell me what the answer was. We're like, oh, we're all going to be electrical engineers, right? And they're like, oh, yeah, we're going to be electrical engineers. And they're like, oh, well, what do electrical engineers do? And we all just kind of look at each other. They make money, right? Oh, yeah, they make money. That's why we're doing this. Now I remember. Capitalism, that's right, that's right. And so it ended up with me being very bad at my engineering classes, because you go to a lab and like shit has to work in the lab. You like go to physics lab and like stuff has to work out. You know, I need this amount of it's like a Mythbusters episode. You have to make stuff that works. You know what I mean? And I'm the person that was watching that they had Mythbusters when I was in school. This was in the 80s, so we didn't even have television, right? So I'm just kidding, we had television. It was just very bad. So back in time, like I would be watching Mythbusters, and like they do the Mythbusters Pirates of the Caribbean, right? Where they invert the boat and then like they like go underwater and stuff like that. You realize that you didn't have to try to do that. I mean, you couldn't make a show out of this because it just becomes a math class. I'm like, oh, if the boat will hold 2,000 pounds of water, then you will need 2,000 pounds to pull it down, right? And I don't think Orlando Bloom and Johnny Depp weigh that much. They are not that dense. Problem solvent. It'll just float there, right? It'll just float, and they'll be like their legs will be dangling underneath. Right? Right. They just have to like you need more weight, you need a lot of Orlando Blooms. And you would also need to weight them down because last I checked, Orlando Blooms will actually float as well. So they had to have guys in scuba gear with weights on, and the boat was just full of water and they were just carrying it. So that's a math problem. You can just calculate how heavy they would need to be to do that. You just calculate it. But they're like, oh, that's not making a good show, right? No one will watch some dude do math for, oh, that's embarrassing for you all. All right, well, we better get out of here. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day. Don't do an experiment when math will suffice.